Bismillahirrahmanirrahim. Assalamu alaikum students. Last time we were discussing Gauss's law. So we said Gauss's law says closed integral E dot dA is Q by epsilon naught. This is net electric flux through a closed Gaussian surface. Q is net charge inside the Gaussian surface. Then we discussed applications of Gauss's law. Applications of Gauss's law or Gauss's theorem. So one application we did was electric field due to a point charge, right? And we showed that electric field due to a point charge is 1 by 4 pi epsilon naught Q by r square. Now today we're going to discuss second application, that is electric field due to an infinite line of charge. So today we'll discuss this application first. Electric field due to an infinite line of charge. We will derive expression for it using Gauss's law. First thing you need to know, we can have continuous charge distributions, right? Charge can be distributed in one dimension, like this line can be charged positively or negatively. This is one-dimensional charge distribution. One-dimensional charge distribution. Now, in one-dimensional charge distribution, we define a quantity lambda called linear charge density, or it's called charge per unit length. So its SI unit will be coulomb per meter, right? So every one-dimensional charge distribution is characterized by linear charge density or charge per unit length. It can be constant or variable. If it is constant, that means lambda everywhere is same. Every unit of length contains the same amount of charge. If it varies, then different units of length will contain different amounts of charge. Likewise, charge can be distributed in two dimensions. For example, I can have some surface containing charge, so positive or negative. Then if surface contains charge, this is two-dimensional charge distribution. Here we define a parameter denoted by sigma, which is called surface charge density. It is actually charge per unit area in the surface, as its SI unit will be coulomb per meter square. And again, this surface can have constant sigma or variable sigma, right? Similarly, we can have charge distributed in certain volume, which will be three-dimensional charge distribution, right? It is characterized by quantity denoted by rho called volume charge density. Charge per unit volume available in the given volume. Its SI unit will be coulomb per cubic meter. It can be constant or variable like lambda or sigma. Now we move back to our topic. We have to find electric field due to an infinite line of charge. So we have line of charge. So we are concerned with one-dimensional charge distribution. So we will have lambda. Let's move to our topic. So consider an infinite line of charge. When I say infinite line of charge, then I cannot draw that on my board or in the screen. So I have a line of charge, infinite line of charge. That means this end is going to infinity, this end is going to infinity. This is a section of that which I have drawn. So let there be positive charge on this line and let lambda be constant linear charge density. So let lambda be its linear charge density, which we assume to be constant. Now we want to find electric field due to this line of charge, infinite line of charge at some point r distance from the line. In order to do that, first thing is to construct Gaussian surface. As you know, so I construct a Gaussian surface in the form of erase it in the form of a cylinder. Let me fix this first. In the form of a cylinder, which is coaxial with the line. So this is my cylindrical Gaussian surface coaxial with the line of charge, right? That means axis of cylinder is coinciding with the line of charge. Let R be its radius and HB its height, right? H is the height of Gaussian surface and R is its radius, right? This I can show R here also. Now this is positively line of charge, so electric field will be outward. Now if I show a patch of area on the curved walls of the surface dA, that will be outward like this, and E here is also outward. Same is true for all patches of the curved walls of the Gaussian surface. So applying Gauss's law, closed integral E dot dA is equal to Q by epsilon naught. It will be my first. Now, first I will evaluate left hand side. Now I can write this flux. I can separate it into three parts. E dot dA upper end cap plus E dot dA lower end cap plus E dot dA curved walls. So I've separated my Gaussian surface into three parts: upper end cap, lower end cap, and curved walls. Now electric field at upper end cap and lower end cap, since electric field is this way, perpendicular to the line, so no line of force will penetrate through the upper end cap or lower end cap. That in other words means this area vector here is upward, and any for whole end cap these area vectors will be upward, and for lower end cap they will be like this. So there will be 90-degree angle between the electric field and area vector. There will be 90-degree angle between electric field and area vector for these end caps. So flux for upper end cap and lower end cap will be 0, because cos 90 is 0. So I will have 0 plus 0. So only curved walls will contribute to the flux through the surface. And for curved walls, see, E and dA everywhere are parallel. So this E dot dA will become EdA. Then I can factor out E outside the integral, because all portions of the curved walls are equidistant from the line. Field strength will be constant. So I will have closed integral E dot dA is equal to Ed dot dA curved walls, which is simply, first I write EdA curved walls. So dot product goes. Then I can write E outside, then dA curved walls. Now this is just the surface area of the curved walls, which is 2 pi RH. 2 pi RH is the surface area of the curved walls. So this is the surface area of the curved walls. So I have calculated the net flux through my Gaussian surface. So I've calculated the left hand side. Now I move to the right hand side. Right hand side contains net charge inside the Gaussian surface. Now this Gaussian surface encloses only a portion of the line. That portion has length h. Since lambda is the linear charge density, therefore the charge contained in length h of the line is lambda h. So my Q is lambda h, right? Using second and third in first, using second and third in first, we get, first is this, I get or we get E 2 pi RH. Instead of Q, I will write lambda h, then there is epsilon naught. So it is simple. Left hand side is E 2 pi RH and Q is lambda h. And epsilon naught is there. So what I get, this h will cancel out. So I get E is lambda by 2 pi epsilon naught r. Let this be my 4. H will go, 2 pi r will come down. So lambda by 2 pi epsilon naught r. So if I am r distance from the line, there will be this much electric field. So it is proportional to linear charge density and inversely proportional to the distance from the line, right? And direction is perpendicular to the line outward if it is positively charged line, negatively charged line, then it is inward and perpendicular, right? So now you can say why we calculate electric field with an infinite line of charge when in reality we can't have an infinite line of charge. So idea is, if I have a finite line of charge and if my point of observation is close to the line and away from the ends, I repeat, if I have finite line of charge, that means line of charge with certain length, but my point of observation for electric field is close to the line and away from its ends. And for that point, that finite line of charge will behave like an infinite line of charge approximately, and this equation can be used as a good approximation for that case also, right? Then I will move forward to third application. So my third, I'm using these numbers 1, 2, 3 or Roman. Okay, 1, 2, 3. So My third application is electric field due to an infinite sheet of charge. Electric field due to an infinite sheet of charge. Now I have sheet of charge, infinite in extent, so there will be sigma, surface charge density involved. So I draw a section of that infinite sheet. So let this be section of that infinite sheet, right? Let it be positively charged. So it is positively charged, right? So electric field will be perpendicular to the sheet, outward. I want to find electric field from the sheet r distance from the sheet, right? So let sigma be the constant surface charge density, surface charge density of the sheet, which we assume to be constant. I have to construct a Gaussian surface. So I construct a Gaussian surface like this. Understand this figure. So my Gaussian surface is in the form of cylinder, but this cylindrical Gaussian surface is penetrating through the sheet. Part of it is to the left of the sheet, part of it is to the right of the sheet. This is my cylindrical Gaussian surface piercing the sheet, and let its each end cap be r distance from the sheet. That means this is r. Let me use another color here. This is also r, right? So each end cap is r distance from the sheet, and let A be area of cross section, right? Now applying Gauss's law. Applying Gauss's law, closed integral E dot dA is Q by epsilon naught. Let this be my first. So again, I split this flux through the surface into three parts. E dot dA curved walls plus integral E dot dA, right now left end cap, plus E dot dA right end cap, right? Now see, electric field is outward, so only end caps will contribute to the flux. Here electric field is this way, and Area vector is also this way. Here electric field is this way, and area vector is also this way. So curved walls will not contribute to the flux because electric field and area vector will be at right angles. Cos 90 is 0. So this term will be 0 and all the end caps will contribute. So I will have closed integral E dot dA, curved walls will be 0. And again for these end caps, E dot dA will become EdA, and E can be factored out because E will be constant over the end cap. So I will write it this way: E dA left end cap plus E dA right end cap. Now integral dA left end cap or right hand cap will just become area of cross section of the Gaussian surface A. It will become EA plus EA, which is 2EA. So I have calculated the left hand side of Gauss's law. Let this be my second in this particular application. So I'm numbering equations application wise, not in overall lecture. So I have calculated this left hand side. What about Q? Q is charge contained inside the Gaussian surface. Now this Gaussian surface is penetrating through the sheet and it will contain only that portion of the sheet which has area equal to area of cross section of the Gaussian surface. That will contain how much charge? Sigma A. So my Q is sigma A. Q is sigma. So substituting second and third in first, we get. So I have to write 2EA on this side, sigma A by epsilon naught. This is 2EA, Q is sigma A, and downstairs there is epsilon naught, right? 2EA, I have used second and third in first. This is my first. Now what will happen? A will go, I will get E equal to sigma by 2 epsilon naught. Let this be my equation 4, right? Sigma by 2 epsilon naught. So electric field due to an infinite sheet of charge is sigma by 2 epsilon naught, where sigma is surface charge density of the sheet, which we have assumed to be constant. Now see, there is no R dependence in E. That means it is independent of the distance from the sheet. That means it is uniform in space. So it's important. It is independent of the distance from the sheet. Distance from the sheet, right? Only proportional to sigma. And another thing which we need to remember is that if we have a finite sheet of charge and our point of observation is close to the sheet and away from its ends, then for that point, that finite sheet will behave approximately like an infinite sheet of charge, and this equation can be used as a good approximation, right? So these were two applications which we discussed today. Now I will give you some homework. Use some simple questions. This is a good question. Your question is, two positive charges, two positive charges, each of each 4.18 microcoulomb, 18 microcoulomb, and a negative charge minus 6.36 microcoulomb are fixed at the vertices at the vertices of an equilateral triangle of side 13 centimeter. Find the electrical force on the negative charge. I repeat the question. Two positive charges, each 4.18 microcoulomb, and a negative charge, minus 6.36 microcoulomb, are fixed at the vertices of an equilateral triangle of side 13 centimeter. Find the electrical force on the negative charge. Remember, know it. I just remind you, 1 microcoulomb is 10 raised to power minus 6 coulomb, right? So this was my question first. I will give you second question. Now question second. A certain charge Q is to be divided into two parts, divided into two parts, Q minus Q and small q. What is the relation of Q, capital Q, to small q, if the if the two parts placed at a given distance, placed a given distance apart are to have a maximum Coulomb repulsion. I repeat the question. A certain charge Q, capital Q, is to be divided into two parts, capital Q minus small q and small q. What is the relation of capital Q to small q if the two parts placed a given distance apart are to have a maximum Coulomb repulsion? So do your homework. This is all for today. Thank you. God bless you. Assalamu alaikum.